Hello everyone. In the previous video, I had obtained this form for the LHS1. So I'll start off this video by writing the expression for the LHS2. So let me just go back to that page where I had the initial expression for this LHS2. I'll just copy it from here. Okay, so this is my LHS2, and unlike the LHS1 where I had gone into a full-fledged derivation, I won't do it here. Instead, I will just write down the final expression that I want, that I arrive at after doing the various manipulations, and that is in this form. So I have the cyclic integral terms just like I had the ones in the case of the LHS1. So please note that there is no magic going on here. It's just that I have written down the final expression on a piece of paper separately, and I'm just copying it from there. Okay, because I want to invest the time that is there in this video lectures, not on these repetitive kinds of derivations, rather on some of the more important and interesting parts of the derivations. All right. Okay, so this is the part which comes with the dy in exactly the same fashion that we obtained the part with the dy earlier, and the next one with the dx will come with a minus sign. Please note that this minus sign is very much present within this square bracket, but of course outside this these first term. Okay, so for that we have this. Okay, so these terms that I have just written down, these are basically my boundary terms. Okay, because you note that this integration is over the entire periphery of the plate under consideration. The next terms that I'm going to write, they will be pertaining to the entire domain. So we had equivalent terms or corresponding terms for the entire domain for the LHS1 also. Okay, now for our subsequent step, of course we are going to write down the RHS. Let me do that first. It will take only half a minute. So for the RHS, I am concerned with these traction terms and these for the problem at hand, or for the general situation at hand for our theory, for the sake of our theory, is this Q is the distributed load. As a special case, we could consider point loads also using the Dirac delta functions. Anyway, so we have this load on the plate acting in the z direction, which is why this is multiplied by this delta W, the displacement in the z direction, and this integration is over the entire domain. Okay, so we have this LHS2 here. In the previous page, what we had, this was basically our LHS1, and together, if you consider this LHS and the RHS together, you will see that back here we have the presence of these terms within that are over the entire domain. Okay, this integration is over the entire domain. This is from the LHS1. In our current page here also we have from the LHS2 these terms which are over the entire domain, and on the right hand side I have this term also which is over the entire domain. Now it is these terms which are over the entire domain which will extract out and which will contribute to the governing equations. The terms which are under the cyclic integral both in the LHS2 as well as in the LHS1, if I just go back there, in the LHS1 you see that I have these cyclic integral terms. Those are applicable on the boundary or the periphery. Okay, so I have to actually go about extracting all these terms. All right, so how do I go about extracting? So the principle is the same. You note that if I go back to this LHS1, considering these terms over the entire domain, you see I have certain terms which are the coefficients of delta US. I have some terms which are the coefficient of delta VS, and I have certain terms which are the coefficient of delta W. All right, these are the various terms which are going to contribute to the governing differential equation separately. It is also important to note that in the LHS2, in the term involving the over the entire domain, there are no contributions or there are no coefficients of delta US or delta VS. We only have the contributions in the form of the coefficient of this delta W. So it is this term which is going to get clubbed with this term here, because this is the coefficient of delta W, and this LHS1 and the LHS2, they are going to come together, but this coefficient here and this coefficient here, they're going to stand alone. Okay, so first of all I'm going to extract this out. So what I'm doing is this. I am considering LHS1 plus LHS2 is equal to RHS, and then I have these entire terms, these huge terms, but from the LHS1 I just have this term which is the coefficient of delta US. So that alone is going to give me, okay, so for my governing differential equation, okay, I will have that first that coefficient term del nx del x. Let's take a look at that again. Del nx del x plus del nxy del y. That is equal to 0. For the next one, let me go back to that page again. Let me pick up the coefficient of delta Vs. This is del ny del y plus del nxy del x. So I'll write the nxy term first. Please note that there is a certain niceness about these equations. I say niceness because this nx, ny and this nxy, they are basically defined on the basis of the stress terms, and you see these seem to be of that very same form that the stress equilibrium equations are from our studies in applied elasticity. So back then we had del sigma xx del x plus del sigma xy del y is equal to 0, at least for the 2D case, and then we had del sigma xy del x plus del sigma yy del y, and it is exactly in that form. Okay, of course these are integrated terms, so there is a certain niceness. That's what I said that. Next, however, it's not going to be so nice, because you see here I have this huge term. In fact, it is so huge that I will not write it. I'll not try to write it like that, rather I'll just copy it from here. Okay, this is the coefficient of delta W from LHS. I'll put it here. So this is the contribution from the LHS1, and then I'll extract this I'll extract this part out. Now, before I do that, I'll have to be a little bit careful in noting that here, although I have extracted it out, there is a minus sign sitting outside this integration. It didn't really matter for this term and this term because they were just alone. Whether I put the minus in front of that and the minus in front of that didn't really matter. But because I'm going to club this term with the coefficient of the corresponding term, there is the coefficient of delta W in the LHS2, that the minus sign really matters. Okay, so there is a minus sign present here. Now let's see here. Here also we have a minus sign outside, so it's good. Okay, so everything has the same sign. So I'll just copy it here. So this is that entire thing. Okay, so this part is coming from the LHS2 and this comes with a plus sign. You can put the bracket here. Okay, and I'll just adjust it a little bit because I do have to put the equal to 0 on the right hand side. Okay, all right. Now what we are going to do next is to try to simplify this third equation, and to do that we are going to utilize the information which is present in this first equation and in this second equation, and you see that can be easily done. So I have this del nx del x over here, then I have del w del x plus nx del square w del x square plus again the same thing over here, del nxy del x del w del y plus nxy del square w del x del y. Now dealing with the second one, I have del ny del y del w del y plus ny del square w del y square plus from this I have del nxy del y del w del x plus nxy del square w del y del x. So I'm done with these terms, both these terms, and whatever is remaining here is just there. So I'll just copy it here. All right. Now you please note that this term and this term over here, they can be clubbed together because both of them involve the del w del x. And if I do that, this so let me just copy this thing, or rather, since I have the presence of these terms, I can maybe skip a step and try to cancel these out in this fashion. So I'm going to consider this term together with this term and this term. So together they will have this del nx del x plus del nxy del y, which is nothing but 0. Next I will have this term together with this term. You see that is going to give me a 0. So what I'm left with are these terms, this one, this one, this one, and this one, this one, this and this. And note that this and this is basically the same terms. Okay, so in the next step, what I can do is I'll anyway copy this thing, but I will skip a step. Let me make this a little bit smaller. So what I'm left with now is nx. I think I have missed something very important. Let me just go back here, and I need to note here that I have actually missed out this RHS. Okay, so that's very, very important, and it's a horrible mistake. I'll correct that immediately. Okay, so if we just take a look back on the RHS, we have this Q delta W. So the term that we really need here is this Q. Okay, so I should be putting not a 0, rather a Q here. Okay, so these are the terms which are the coefficients of delta W. This Q also is that from the RHS. So that's it. So major correction here. Okay, similarly here there should be a Q. All right, now I have this nx del square W del x square. Then I have this one, but I'll club this one and this one. So together I have twice nxy del square W del x del y plus this ny del square W del y square, and then I'll have these terms. All right, now this particular combination, it had appeared in our previous chapter also, and if we follow the exact same steps, what we are going to obtain is this expression. Okay, so this entire thing, if we write in terms of the deflection W, it is going to be minus D pi harmonic of W. Okay, so overall what we are going to end up with is this. We have this, of course, that much, then we have minus D del for W is equal to Q, and let me put a therefore here. Okay, now what we are going to do is to write this nx, this nxy, and this ny in a very special form. Not something which is completely alien to us, but something familiar definitely, but in a rather surprising way. So one might wonder what is the motivation for doing such a thing. So we'll see the advantages of that going forward. I mean, Keeping it in this particular fashion, I mean, it's absolutely not wrong, but we do want to recast this equation in a more convenient form. Let's put it that way. So what we're going to say is that, you see, this nx is basically coming from the sigma xx, this nxy is coming from the sigma xy, and this ny is coming from the sigma yy. Now, what we have done in this chapter on the Föppl-von common theory of plates is exactly the same thing that we had done back in our classical plate theory, the previous chapter, and that is by integrating through the thickness of the plate from minus h/2 to h/2, we have effectively reduced what is essentially a 3D problem to effectively a 2D problem. Okay, that is the net result of doing that integration. So we have effectively reduced it to a two-dimensional problem, which is why we are only left to deal with this sigma xx or the terms in originating from the sigma xx, sigma xy, and the sigma yy. Now, what is the next step that we're going to follow has its motivation in that effective two-dimensional reduction, which is to say that back in applied elasticity, when we were dealing with the 2D elasticity chapter, we had expressed the stresses in terms of a single scalar function in terms of its derivatives using the eddy stress function, and we are going to do a thing which is exactly the same. So we write this nx, nxy, and ny in terms of this scalar function. Okay, so let me go to the next page. In terms of a scalar function, which is like a stress function, but it is not directly a stress function, because you note that these are not directly the stresses, rather these are the integrated forms of the stresses. Okay, so in terms of a scalar function, capital F. Okay, so what we say is that nx is equal to del square F del y square and y is equal to del square F del x square, and nxy is equal to minus del square F del x del y. So this is reminiscent of what we had done in applied elasticity, where we had written sigma xx is equal to del square phi del y square, sigma yy is equal to del square phi del x square, and sigma xy is equal to minus del square phi del x del y. Okay, so if you do not remember the discussion around this eddy stress function, I suggest that you take a look back at that video. I'll put a link to that video in the details of this particular video down below. Okay. Now with this choice, what we can do is we can take this equation and rewrite it in terms of this scalar function. So therefore, this thing becomes del square phi F del y square del square W del x square minus twice del square F del x del y del square W del x del y plus del square f del x square del square w del y square minus d pi harmonic of w equal to q. All right. Now, some of you may be wondering that because we have now introduced another unknown, is it really true, and the unknown is in the form of this f, is it really true that we have ended up simplifying it, or have we really made it more complicated? But please note that earlier we had this nx, ny and nxy, so those were unknowns also. Okay, so we had these three unknowns, but by making this clever choice to rewrite them in terms of the scalar function, we have kind of made it more manageable. Okay, but we'll really see the truth about how manageable it has become or not as we proceed. But as things stand, this particular equation does contain two unknowns. The first is the deflection w, which we do not know about, and the other is this unknown scalar function f. Okay, so we have one equation in our hand. This is a governing differential equation, no doubt, but it contains two unknowns, w and f. So it is now our responsibility to generate, so to speak, or to determine another governing differential equation, so that we'll have simultaneously two equations and two unknowns, so that the system becomes closed and we can actually solve for the unknowns. And that we'll do in the next video. Thank you very much.